This is SecuriGen. It is a system that uses GPT-4o Mini to build its own honeypots, deploy them, and rewrite them based on the attacks it catches. Over the past 3 months, it has logged almost around 20,000 real attacks from the open internet. And let me show you how it works. Most LLM honeypot research calls the model in real time for every single request an attacker sends. This approach is slow and expensive, which is why SecuriGen does the opposite. The LLM only runs twice, once to generate a complete standalone Node.js honeypot from a CVE spec, and once later to evolve it based on what actually got attacked. After that, the honeypot runs completely independently. There are 0 LLM calls per request, and the only thing running is the generated code. Now I'm going to deploy a honeypot live that targets 2 real vulnerabilities. But before that, I just want to clarify something. The front end, I'm running it locally, and the backend, I have deployed it to a Linux server on the cloud, so a DigitalOcean droplet. And the reason for this is that I don't have the computational power to open my whole project up to the public. Of course, the backend is open to the public. They can attack it, but they cannot access the control panel itself. So with that out of the way, let's create a new honeypot. I'll choose backend. As you can see, there are CVEs vulnerabilities available. I'll choose Spring for Shell, which is a remote code execution bug in Spring MVC's data binder, and the actuator exposure CVE, which is just attackers can use Spring Boot's diagnostic endpoints to leak environment variables and the config files if you're not careful. So the name is optional. We click deploy. So this just started an async pipeline. GPT-4o Mini is right now writing a complete Express app that includes routes, fake responses, and everything. And once that comes back, the Java backend uses Docker to build an image and spin up a real container. It should take anywhere between 15 to 30 seconds, maybe even faster. Oh, it got done faster. So it's deploying right now. You can see it's running, and the endpoint is at 8080. So this means we are live, and the honeypot container is now genuinely listening on port 8080. So a little fun fact about this, originally the central Spring Boot backend, the control panel was listening on 8080, but I configured it so that the honeypot listens on 8080 and the control panel listens on 8081. This is because if an attacker is targeting a Spring Boot server, they're going to scan for 8080, and the honeypot is supposed to be the thing that takes all the attacks. That's why the honeypot is on 8080 and the central server is on 8081. For every honeypot, this is the honeypot that we just created. For every honeypot, we can go to the generated code tab and we can look at the code that was generated by the model. So no human touched this. This is all AI generated. And at the top of every code, you can see the logging middleware. This is code that is responsible for reporting every incoming request to the ingest endpoint. So basically the central backend of all the honeypots. Now I inject this code into every prompt so that every honeypot reports attacks in the same way. And below it, you can see the routes for the actuator endpoints and the Spring for Shell parameter handling. This is straight from the CVE spec that I gave it. So basically, all you have to do is give the CVEs or the vulnerabilities to the backend, and the backend will look at it and it will generate the code accordingly. These are all the fake paths and the fake responses that the honeypot gives back. If you're interested in the prompt that was used to generate this code, you can look at the backend repository of SecuriGen. It's all in there. Now let's actually attack the honeypot using this script I made. We can see that this script fires the exact payload that Spring for Shell scanners use. You can see the class.module.class loader, this long payload. This is what's used in an actual scan. I also included actuator probes that are used in an actuator exposure attack. And on top of that, I also added some paths that are not included in the base code generated by the model. So you will see in a bit just why. So now let's run that script by giving it the exact IP address of the honeypot. The green ones are the paths that are handled by the honeypot. The red ones are the additional ones that I gave. These are the ones that you will see why this is, this is given. So red ones are 404s. They're not handled by the honeypot. Right now it's still attacking, and you can see the attacks happen in real time. 22 hits. My IP address is exposed, by the way. I will censor it when I edit this video. But you can see that the information, like additional information, is given. The the uh, the payload that is delivered in these attacks is visible here. Also, while the honeypot was running, we got attacked by some different addresses. Some addresses in the United States, some in France. So you can see that's just the honeypot doing its job. Let me just see if it's done executing. Yep, the attack is done, and right now you can see the coverage score is pretty low, but that's because I deliberately hit some points outside what it was told to build, and you will see why in just a bit. Now for the interesting part of SecuriGen. The evolve function takes the last 50 attack logs. It splits them into paths that returned a 404 and paths that already worked. It then takes the code that already exists and the split paths, and it feeds them back into GPT-4o Mini, and it gives it one instruction: cover every unhandled path and don't break what already works. So let's trigger the evolve function right now. Right now it's rebuilding the container with the same port but brand new code. However, this new code is shaped by what actually got attacked. As I said before, the code is given and the prompt is given, and now it's gonna evolve. So I'm just gonna speed up this part. Okay, so the evolution has finished, and you can see it's way longer now. So this is generated using the insights from the previous attacks. Now that the evolution is done, I'm going to run the exact same script again, the same attacks in the same order. However, this time you can see a difference. The first one had 9404 responses. This one has 0. This means that the honeypot, it's the same attacker traffic, but the honeypot taught itself to handle paths that it had never seen before an hour ago. Now, on just one example, it's not significant, but imagine this with hundreds of evolutions over time. This can learn, thousands of attacks, and it adds to the same code base. So that's the main feature. So a couple of things happening under the hood that are worth mentioning. The first one is that the honeypot container only talks to the backend over an isolated Docker bridge network. So the logging endpoint is never exposed to the internet. As you can see here, the logging endpoint only talks to the honeypot containers. So the only port that's exposed to the internet is the honeypot's port. So number two is that there are two completely separate secrets. One accesses the dashboard, so it's a separate one, and one is for the containers reporting logs, so that when one channel is compromised, it does not automatically compromise the other one. This isn't just a local demo. This exact system has been running on a virtual machine on DigitalOcean for 3 months. It had no supervision and logged almost 20,000 real attacks from actual internet scanners. Across two evolution cycles early on, the number of attacks it could meaningfully respond to went up from 8 to 82 to 97. Coverage percentage, although, actually looks lower now than it did back then, and that's expected because the more scanner traffic you get, the more brand new and unseen paths show up. So the raw percentage drops even as the absolute number handled keeps climbing, which is why I track both. And ladies and gentlemen, that was SecuriGen, an honest attempt at proving that LLMs can build and improve their own deception infrastructure without needing to think in real time. The code is on GitHub and the link is below.